It is my pleasure to introduce today's LOF&BE speaker. So this is the LOF&BE webinar series. I'm Sarah McAllister. I'm hosting these with Sam Manzello and Sayaka Suzuki. And I'm very pleased to announce today to introduce Pedro Reszka as our speaker today. He is a mechanical engineer with 20 years of experience in combustion science and several aspects of fire safety engineering. Since obtaining his PhD from the University of Edinburgh, his work has focused on material flammability, with works expanding the classical ignition theory, development of new flammability apparatuses, and on wildfires in Mediterranean ecosystems. He's an associate professor at the Universidad Adolfo Ibáñez in Santiago, where he additionally serves as the director of the mechanical engineering degree. Dr. Reszka has participated in fire safety engineering, standard development, risk analysis, and incident investigation projects in Chile, Peru, Colombia, the US, and the UK, with a priority on the mining and gas industries. And with that, Pedro, I'll let you have at it. Take it away.
Thank you very much, Sarah. I hope everybody's listening okay. Thank you, Sayaka. Thank you, Sam, for inviting me here. It's a nice opportunity. It's really a privilege to be able to tell you and share with you what we've been doing here in Chile. I have structured the talk essentially in 4 parts. So the first part, and I always try to do that. I don't know. I feel we're a bit kind of far away from the world. So I'll just show you some quick facts about Chile, the wildfire situation, and the work that we've been doing in our particular research group. And then I'll just share with you 3 examples of recent results that we're going to be presenting in conferences in Portugal and in the Combustion Symposium in Vancouver. So I'd say that the most important feature of our country is that we're a really thin and long country. We're the southernmost country in the world. But most importantly, we stretch several decades in terms of latitudes, and that makes us have a very varied climate and landscape, which we'll see in a few minutes. We've enjoyed a good economic situation in the past decades, and you know we've been progressing, at least in our neighborhood. We're better off probably than most of our neighbors, and we're very proud of that progress. The most striking features in terms of topography are the 2 mountain ranges that go from north to south. So we have the Andes Mountains, which are the second highest mountain range in the world outside of the Himalayas, and there is a lower altitude mountain range, which we call the coastal range. In between, particularly in central Chile, in between these 2 mountain ranges is a central valley, which is famed for wines and other agricultural products, and that is where most of the population lives. So in a stretch of 1,000 kilometers approximately, most of the population of Chile's population is concentrated. We're about 19 million people. And with as I mentioned, with this important change in latitudes, we have essentially 5 distinct natural regions, and I'm going to show you some exemplary pictures here that I've taken. The far north, of course, is characterized by the driest desert in the world. As you move a bit further south, we call it the near north. Of course, everything is centered around Santiago, the capital city. And there you have a higher presence of vegetation. Central Chile, on the other hand, is a Mediterranean climate. It's characterized by shrublands, savannas, like shrublands like you can see here. Sometimes you have higher elevation shrubs or trees, but also by the strong presence of the paper pulp industry, which keeps large swaths of land with forest plantations. These are mainly pine trees and eucalyptus plantations. As you move further south, the weather becomes more temperate, the climate becomes more temperate, I'm sorry. And so you have colder weather, greater amounts of precipitation, and until you hit Patagonia with the impressive landscapes dominated by glaciers, mountains, fjords, etc. In terms of the vegetation, and here I'm going to focus on the vegetation of central Chile, which is where the forest fire problem is focused. As I mentioned, we have naturally shrubland forests and savannas, grasslands. But in the recent, probably in the past 100 years, we've had also a large parts of the country, of that part of the country, which are covered with plantations. You can see that the forest plantations here, the dark green colors are where there's a higher presence of forest plantations. You can see that these are located in the coastal range, but towards the coast, towards the Pacific Ocean. On the other hand, native forests, well, you can see that they go from essentially from Santiago to the south, and these are covering all the rest of that southern part of the country. We've had a persistent drought probably since 2010. You can see here this precipitation index. It's a paper by people in Universidad de Chile. And you can see that we've had as low as 50% of normal precipitation in this past decade. Some people say already that that climate has changed, and so that this is going to be probably our new normal. So we're probably going to be experiencing half of the historic precipitations that we had, particularly in this part of the country. You can see here, again, this is a cumulative drought/heat wave index, and you can see that the Central Valley is particularly affected by this drought. In terms of the wildfire situations, our fire season is markedly occurring during the austral summer. Remember that we have the inverse from the northern hemisphere. Everything points to the fact that the fire season length is increasing. The reason for this can be, of course, the drought, but also probably attributed to climate change. Now, this marked seasonality in our fire season has to do with our Mediterranean climate, the Mediterranean climate that we have in central Chile, meaning that most of the precipitation occurs during the winter, and our summers are pretty dry. This also has as a consequence the fact that we don't experience too many thunderstorms or storms during the summer season. It happens mostly in the Andes Mountains. And so this means that less than 0.5% of all the ignitions are confirmed to be by natural causes. So human activity is the #1 driver by far who is causing wildfires in our country. You can see here in this graph, it's a graph. These are the statistics by CONAF. CONAF is Chile's Forest Service. And you can see that the number of fires has been kept pretty stable. Burned area, the same thing, with this notable exception of the 2016-2017 fire season, which was record-breaking in every aspect. And we will talk a little bit more about that later on. Now, response is done by CONAF, but also by private fire brigades, and these attend mostly to fires in the forest plantations, but also to fires in the surrounding areas, and they collaborate very strongly with CONAF. In terms of the damage patterns are pretty similar as well to the United States and Europe. So we have a really good response, meaning that most of our fires burn a small area, and of course that 1%, those are the big animals that cause huge damage. Again, we're focusing here on plantations because there's an ongoing controversy here in our country saying that somehow these species are more fire prone than the native species. We haven't found any evidence on this, but we're naturally we're looking into that. But these they account for about 30% of the burned area, with the rest being attributed to natural vegetation. The nature of the fire problem at the wildland-urban interface is probably different to what is experienced in North America and in Europe, mainly, in my opinion, by the fact that that most of the neighborhoods that are affected by fires are mid to low income. You can see here this fire from last year, December last year. You can see that the separation distances between the different structures are not large. Gardens are virtually inexistent. Green areas, parks, stuff like that, not available as well in these low-income neighborhoods. The other problem, and this is something that is probably also of interest to people in South Africa, for example, is that we have many fires that affect that affect the WUI, but that affect informal settlements. This is the biggest example is the village of Santa Olga, and we will talk about that later on, which got completely decimated during the Las Máquinas fire during the 2017 season. Now, the problem is that these neighborhoods are non-compliant with the building code, and it's probably very hard, is a problem which is very hard to solve in terms of improving the passive fire protection or the inherent conditions that can control fire risk at this level. Finally, I want to say that there are currently no risk assessment requirements in our national laws or regulations. There are some projects to improve that, but the current political situation in our country makes political consensus hard to come by, essentially. Here's a list of some WUI fires that I've collected. Statistics are also hard to come by in terms of number of structures affected. That's also something which we're lagging behind with the Northern Hemisphere. I want to just highlight the Great Valparaiso fire in 2014 and the fires of 2017. Finishing this introduction, I just want to show you a little bit about who we are in terms of our research group. We work very closely with Universidad Técnica Federico Santa María. They are the largest group in Chile working in fires and combustion. We're part of Universidad Adolfo Ibáñez. The effort, I have to say that we're thanks to the leadership and the hard work by my friend and mentor, Professor Andrés Fuentes at USM. We're also one of the few research groups which are carrying out fire science, broadly speaking, in Chile and in South America. If we started as a group of engineers, now our team is become really multidisciplinary. We have scientists from different fields, including biochemistry, ecology, agricultural science, and of course engineering. We have tried in the recent years to focus our research into this new concept of pyroecophysiology. Okay, so we're trying to link not only the combustion side, the fire side of the problem, but also the ecophysiological side of the problem, which is, it's a big universe in itself, and that's why we have really good professionals working there. We've had several successes. We've secured several $1 million in Chilean science funds. We have close collaborations with people in Europe, the United States, Brazil, Australia. Several of our students have pursued and are pursuing PhDs currently in universities in the Northern Hemisphere. We formed, and we're very proud of that. We formed the Chilean section of the Combustion Institute, and by the way, we're holding the second summer school in December this year, which we will focus on wildfires. The focus of our research, if you think of the length scales defined by Cerro-Guillaume, the focus of our research essentially covers everything. We do both fundamental and applied research, and in the remainder of my presentation, I'm going to focus in three aspects. Essentially, the work that we've done on thermal ignition theory and bench scale testing. Then I'm going to present some work on quantitative risk analysis. And finally, we're going to present some work, some recent results we've had on remote sensing. So I think everybody agrees that experiments are still a fundamental part of research, particularly to understand all the underlying mechanisms that control fires in general, of course, wildfires in particular. And you probably have, there's essentially two ways to carry out experiments. You could do large-scale testing, but also there's also the option of doing bench scale testing. We have chosen to follow the bench scale testing avenue. We believe that even though large scale tests are really important and significant, they have some disadvantages that, particularly in our part of the world, they're probably really hard to overcome. These have to do, of course, with high costs, repeatability issues is something important. I'm going to mention it in the next slide. Carrying out diagnostics from our past history, when we got trained in Europe, we pretty much favor laser-based diagnostics and detailed high-resolution diagnostics, both temporary and spatially resolution, and it can be a challenge to perform those large-scale tests with such a resolution. And finally, following Professor Torero, the question remains whether the scale of the fire test is still able to capture all the relevant interactions between the flame, the fuel, and the environment. So we chose to carry on this avenue on bench scale testing. This is a cube which we've been working on for a few years, and it's essentially our opinion regarding what the ideal bench scale test should be like. So in terms of the ideal test, we believe that it should, of course, subject the specimens to realistic fire conditions. The boundary conditions should be quantified, and of course we should be able to carry out in situ optical laser-based diagnostics, both on the flame and on the solid phase. You can see that since the 1940s, the progress has been considerable, particularly during the 1970s and 1980s, with the development of all the standard fire calorimeters that are in use today, and it's a hats off to all the people. I have to mention that it's not only the progress has not only been due to the fact of technological advances, but also, of course, and mainly due to the fact that our understanding of fire phenomena has increased considerably in those decades of the 20th century. So what we have been working on in the past years has been to try to move forward and move to the next block within this cube. We've developed two types of apparatuses. The first one here is the idealized firebrand ignition test. It is it's a test to we do it to test samples on what we call discontinuous ignition, meaning landing of a firebrand on a piece of porous material, and then testing for the ignition delay times and heat release rates. We've tried to do as much of a convergence between this combustion chamber and the other one, and this other combustion chamber. This is the sensible heat calorimetry apparatus, and here we use it for what we say continuous ignition, which essentially is heat radiation from the flames. Okay, so they both aim to have equivalent diagnostics. The common features here are that we have full optical access to both the flame and the solid fuel. We carry out inline detection of the combustion products, which brings down the oxygen measurement delay time considerably. We've strived to work on quantifying particularly the convective boundary conditions, because of course the radiative boundary conditions are very well quantified in the standard calorimeters. And we've tried to guide our work with this concept of producing curated data and complying with the 3 R's, which are repeatability, reproducibility, and replicability. And we believe that if we try to follow these concepts, both not only in the experimental aspect of our work, but also in the theoretical and numerical work, we'll be able to carry out better predictions. The work that I'm presenting here is going to be presented at the next combustion symposium. We're working with CONAF, the Forest Service, as a part of a long-term goal of optimizing the use of fire chemicals in Chile. We've applied for funds to develop standard test methods for the certification of fire chemicals in Chile. The thing is that right now we have chemicals in Chile that are being certified by the U.S. Forest Service. There's other types of chemicals that are being certified in Europe, in Spain and France, but there are several suppliers which are not certified, and CONAF wants to know whether these chemicals are safe to use and also efficient in terms of fighting wildfires. So the first tests that we did were carried out on a long-term fire retardant. We did a test protocol which was based on the U.S. Forest Service protocol. We collected Pinus radiata samples. We conditioned them. Then we applied different amounts of fire retardant, and finally we dried these. And these dried samples were tested in the IFIT, meaning discontinuous ignition. The effect of the fire retardant here, the phi equals 0 means no fire retardant, and here as you go with higher phis, that means there's higher relative amount of fire retardant in the specimens. The notable thing here is that there is not too much of an increase in terms of the critical heat flux for ignition. Rather, the curves are displaced upwards, but again, the critical heat flux for ignition, we noticed that it didn't change. We also developed a theory following the work of Kahn, De Vries, and Ogden, where we essentially model the role played by the fire retardant as an additional sensible energy requirement for the porous fuel to reach the ignition temperature. We carried out an integral approach so that the cylindrical geometry, we express the temperature of the whole cylindrical sample using one average temperature. This simplifies enormously, as you can imagine, the energy equation. QT is a net heat flux, which is the difference between the incident heat flux and convective losses. This is following the work by Delicacios. And this solution technique allows us to model both thermally thin and thermally thick samples. As expected, the relationship between the inverse of the ignition time and the incident heat flux follows the classical results for thermally thin solids. And the neat thing about this is that we can obtain effective properties by plotting the inverse of the ignition delay time and the incident heat flux. This integral approach is a very powerful tool. We've used it successfully to model Cartesian and cylindrical geometries. We've also used it to model the penetration of thermal radiation into the specimen, which is it's a very important topic. And in the future, following this work with CONAF, we will be testing other fire chemicals. And hopefully, when we obtain the funds, we will work to develop an improved, in our opinion, an improved test device to certify the fire behavior of specimens with and without fire chemicals. I want to finish this part on bench scale testing also by sharing with you the fact that as part of one of the big projects that we got awarded recently, we're hoping to study the flammability of both live and dead pine needles, but also of stressed and non-stressed vegetation. We're focusing on abiotic stress, which is stress coming from non-living sources, and you can see that we have now the capabilities of extracting chlorophylls and other chemicals, and we will very soon start carrying out experiments to link these with the material flammability, both in continuous and discontinuous configurations. Now we move to a larger scale. And I want to share with you this work that we will be presenting at Coimbra later on this year. The main motivation for this work is the realization that we're one of the countries which is, at least in terms of expenditure and percentage of GDP, we're one of the countries which are most highly affected by natural hazards. You're all aware of earthquakes, volcanoes that we have. We're part of the Pacific Ring of Fire. So it's not only wildfires, but it's also, volcanoes, earthquakes, and tsunamis, but also as well flash floods and landslides. We call it mass removal. Now, there's been a push by the academic world in Chile to try to develop risk maps from multiple hazards. Now, we believe that quantitative risk analysis is a very good way to carry out these analyses, particularly because you can sum up the contributions from each different natural hazard very easily. What is QRA? QRA has its origins in in industries that you can see, which with really high consequences. So atomic energy, chemical process, and aerospace industries. And the neat thing about QRA is that the risk estimates are the result of a combination of both probabilistic and physical modeling. The main features of the QRA are the following. So there is energy which is stored typically as a point source. So think of an oil tank, for example. And so the initiating event corresponds to the release of energy. Now, the outcomes, meaning whether you're going to have a flash fire, a vapor cloud explosion, or just gas dispersion, whatever, these outcomes depend on a series of intermediate events. And these events can you know, they will alter the outcome and the severity of the outcome. And these events are typically modeled using an event tree. And with this configuration, you can very easily calculate the probabilities of each of these outcomes. Now, each outcome, as I mentioned, gas explosion, jet flame, whatever, can be modeled physically. And the goal of this physical model is to understand the magnitude of the physical insult to a specific target or individual. The consequence, therefore, is the link between the physical magnitude of each particular outcome and a damage probability. So if I want to calculate the risk associated with this energy release, I only have to calculate all I have to multiply the frequency by all these probabilities, and I will get the risk for that particular outcome. And finally, the risk for this initiating event is just the summation of all the particular risks. The structure of this method means that you can very easily sum the contributions, the risk contributions for different initiating events, and this you can understand them as different natural hazards. The spatial distribution of risks is essentially given by the spatial distribution of these magnitudes, of these physical magnitudes. So we adapted this methodology to study wildfire risk analysis. And we did it. We applied this to study the risk at an electrical substation in Valparaiso. This is part of a piece of critical infrastructure, so it's very important for the company. And this, as I mentioned, is part of a PhD thesis by Gonzalo Severino, and will be presented in Coimbra later this year. Now, the good thing about this is that it's the methodology is independent of the tool you use to actually model the wildfire spread, and it's something very convenient because eventually those technologies are probably going to change. The main differences, I'm not going to delve too much here, but the main differences, I would say that has to do with the fact that in industrial settings, the hazards, this energy is concentrated at a point, but in wildfires, they are spatially distributed. The other thing, and it can be a flaw, as you will see in the next slide, the other thing is that we base the frequency we estimated based on past human action. So past human performance, we're using it to predict the future human performance, and you can very easily understand that can bring about many problems. On the other hand, industrial settings they typically have equipment reliability databases, and that makes it a bit more structured in the sense of obtaining that frequency. Here is our event tree. We essentially calculated the probability of the fire reaching the WUI, the WUI where the electrical substation is located. The star marks the location of the electrical substation. The event frequency, as I mentioned in the previous slide, we obtained it from historical data, and that gives us 4.6 ignitions per year in this particular portion of the Valparaiso wildland urban interface. To get the consequences, what we need to do is we need to estimate a heat flux on the substation. For that, we converted the fire line intensity to an incident heat flux. Considering those two scenarios, essentially it's different separation distances and different angles relative to the substation. The consequence is something, is where we link this incident heat flux with the failure probability. To do that, we use the probit concept. It's a probit is a short term for probability unit, and essentially what the probit does is that it links the damage probability to a dose of a harmful thing. Yeah, so you can see here. This is data from a very interesting paper by Sabi et al., which was recently published in the Fire Safety Journal. You can see here that at the critical heat flux for ignition, the probability, if you're at the heat flux, you have a given ignition probability, but as you move below to heat fluxes below the critical heat flux, you are still going to have ignition in some cases, but the probability of igniting is slower. And of course, as you move to incident heat fluxes, which are much higher than the critical, almost every sample, and then you're gonna be in the situation where every sample subjected to that heat flux will ignite. Now, this is typical of a phase transition phenomenon, but you can see that here you have a logistic curve here, and this curve you can linearize it with it's a straightforward mathematical treatment, and you can obtain this so-called probit function, which is related to the failure probability. So here we have this linear expression now, where we can get very easily the failure probability as a function of the incident heat flux. We used data by Babrauskas and Ball and Rain, both for wood and PMMA, to build the probit equations for wood and for PMMA. Of course, PMMA will serve as a proxy for all the plastic components in the substation. Having done that, we estimated the risk. These are the values for the wildfire risk at the substation for both ignition scenarios. I still believe that this is a bit too elevated, but we're getting there. Wildfire QRA, if we want to do a wildfire risk map for the whole of Chile, for example, this would the main limitation of this method is that it demands a lot of resources. It's not only time that you need, but also data. So data can be an issue and is an issue, particularly here in Chile. Probit functions also require large amounts of data because you have to obtain that logistic curve, and you have to obtain the ignition probabilities at heat fluxes which are very close to the critical heat flux. And finally, if we're doing simulations, or we're doing an analysis for not for a landscape level, but for a smaller scale, then you probably need to switch from using fire propagation tools like FlameMap, for example, or Prometheus, to using CFD codes, and that can also be an issue. So we're currently working on proposing risk mitigation measures for the substation, and also for incorporating discontinuous ignition at the substation. And so now, if you bear with me a couple more minutes, I'm gonna discuss the third leg of this of our research, and I'm gonna start with just a brief description of the 2017 mainly fire season. This was the most severe fire season on record. We had multiple fires burning at the same time in central and southern Chile. This prompted an international response. We needed to call for aid. Coupled to that, we had record-breaking heat wave. The result of that was that not only that 11 people were killed directly by the fire, but also by a lot of conspiracy theories people were thinking that we were in the middle of a terrorist attack. A lot of things happened during that summer. The total burned area was 570,000 hectares. That amounts to about 1.5 million acres. Of those fires, the Las Máquinas fires, máquina is a machine in Spanish, is the largest single fire in Chilean history that has ever been recorded, of course. 190,000 hectares were burned as part of that, and unfortunately, 5 of the 11 people were killed directly by that fire. And as I mentioned before, the village of Santa Olga was completely destroyed on the night of January 25, 2017. Now, we've had an interest in remote sensing for several years now, and this is work also which is going to be presented at Coimbra, and this is also part of a master's degree thesis by Jorge Valdivia. And so essentially what we wanted to do is we wanted to set up an infrastructure to obtain as much information as we could of all the conditions before, during, and after the fire, using as much of remotely sensed data as we could. We don't have the resources as in more developed countries, so obtaining this type of information, again, as detailed as we can, from open access remote sensing data is very appealing for us. And so we decided to do this analysis using the Las Máquinas fire. So we obtained data, of course, from satellites from NASA, and NOAA, and Finland, I believe this is. And so we focused our interest in this, what we call the region of interest. The fire occurred in the Maule region in central Chile. The region of interest is composed of 5 municipalities. You can see there the names. I'm going to bore you with those names. And the area is mainly rural in the region of interest. A large presence of forest plantations, which are mainly Pinus radiata. We also had some protected forests of endemic beech and palm tree species, and also the native shrub forests and agricultural lands. So I'm just going to very quickly show you some of the results that we've obtained. The burned area we obtained with different products, but this is using the MODIS sensor. The fire had 2 origins, and you can see here that they're marked here, the 2 fire origins. It's roughly here and here. This is how what the official investigation of the fire determined, and you can see that the northern part of the fire covered a much larger area than the southern part. You can see here the cumulative in the blue bars. That's the cumulative burned area, and in the red lines, that's the daily change in the burn area. You can see that between January 25 and January 26, the amount of area that burned was enormous. That matches the destruction of the village of Santa Olga. Here we have a time series of the burned area, and you can see how between January 25 and January 26, which is when Santa Olga burned, the fire grew incredibly strongly. And then after that, you can see that the fire, the growth of the fire was pretty marginal, and it got contained a few days later. The Canadian Fire Weather Index is something which is used to determine fire danger. We calculated it using different techniques. This is shown using MODIS data. This is not entirely with remote sensing. We used wind speed data from meteorological stations. And then we did calculations using Wind Ninja. we obtained surface temperatures using linear regression and machine learning. And you can see that the peak values are here in January 24th. Now, we also did this with VIRS and ERA5. ERA5 is reanalysis data, so it's essentially weather forecasts, but are corrected with the known data. And this, of course, gives you much better resolution in the temporal scale. But we believe that obtaining these estimates with a much better resolution in the spatial scale is also very useful. Fire radiative power, you can see that the peak values are here, January 21st. So the big growth of the fire here, you can also see some spots which are in red. Here, that the fact that we didn't get the highest values in January 25, 26, or 27 are probably due to the fact that the fire emissions were also really high. We had a strong presence of aerosols there at the time. You can see this here. Pyrocumulonimbus clouds were also detected there. In terms of the vegetation, here you can see that the drought, we have very frequent drought periods here. Remember that the persistent drought is from 2010 onwards. And you can see here, I'm going to go very quickly now, that the vegetation after the fire, this is the dashed line represents the time of the fire. You can see that the vegetation here failed to recover in some of the municipalities, particularly Empedrado and Constitución. Vegetation also suffered significant changes. So what happened is that we had a significant loss of forest lands, which can be needle leaf and broadleaf forests, and you can see these here. Yeah, so the red and the orange curves, and we had a strong increment in savannas. And so that's the analysis we've done so far. Another piece of work that I want to mention is that we're working on adapting the Canadian Fire Weather Index to the conditions in central Chile. This is the original Fire Weather Index, and this is our modified proposed Fire Weather Index. And you can see that we have a much better or a better correlation coefficient. And we also we also carried out some approximation for the exponential terms to get a much quicker expression that helps us to carry out forecasts, daily forecasts. So I want to finish the talk, but just by reflecting on how convergent, even though we have different aspects of the problem, but I just want to highlight the convergence between Mediterranean ecosystems. It's not only topography, vegetation, and climate, but also we believe is fire risks. We're facing increased fire risks in all Mediterranean ecosystems across the planet. So I hope that you have enjoyed the talk, and you have thought that this is an interesting work, and we're really happy to collaborate. So I want to thank you, and I want to acknowledge the help and the hard work and the contribution of all these colleagues all over the world, which have helped produce these results. Thank you very much.
Wow, Pedro, thank you for the whirlwind tour of all the different work you guys are doing. It's an impressive range that you've got there, from small scale stuff all the way to the landscape stuff. So
thank you very much.
So if anybody has any questions, feel free to type them in the chat box, or if you're brave and want to be on YouTube, go ahead and unmute and speak up. In the meantime, I mean, it's fascinating. I personally am very much looking forward to your work with the live fuel flammability, because that has been something that has just been so challenging to get any kind of foothold in. So I'm really looking forward to a new take on it. And
well, and yeah, of course, your work has been pioneering as well. So so hopefully we'll so the focus that we're giving right now to that work is that we're trying to determine all the biochemical markers that hopefully will give us some light on on increased or decreased flammability across species and across different states of stress. It's ongoing. We just had a meeting today, so hopefully next year we'll have some answers there.
That sounds pretty awesome. Looking forward to it. You know, and tell anybody else any questions. Sam has typed some comments into the box here. One of them is, I guess, helpful for other people in the room here to know, is that there is an ISO TC92 WG14 working group focused on large outdoor fires. And they've got a lot of members from various countries in the ISO working group, but no members from Chile. So think about getting somebody from over there to get involved, because they're not just on WUI fires, but also informal settlement fires. So that's kind of, you know, a good, like you said, good tie-in to some of those other places like South Africa, that it's a pretty big issue. And it's a global problem with global standards that we need. So yeah, so thanks you very much for the talk. So before anybody else asks questions, again, go ahead, type them in the chat box or speak up, raise your hand. Oh, we might have one. Go for it. Oh, you're muted. You're muted there, sorry.
Okay. Oh, good. I wondered how your work has been used on the mitigation side. The work you did in Valparaiso was very interesting to see what the threat is to the transformer. So how do you translate that information into some sort of action to lower the threat over time?
So we have we still haven't proposed risk mitigation. Of course, the clearing of the vegetation is a very obvious obvious pathway there. So the regulation for critical infrastructure in Chile requires you to actually carry out these types of analyses, and so not only the proposed risk mitigation measures are useful for the company, but also the fact that they have quantified the risk. So I think we're going to probably do again, increasing the separation distance, which could be like a passive fire protection measure. I understand they already have active fire protection in place. But it's something that we still have to analyze more in detail.
Well, I mean, it's a very strong case for I think you should tell the people who are listening that in Chile all the electrical utilities are concessions. They're private companies, and so that the government isn't investing in this mitigation. Who invests is the private companies, which under their concession charter requires them to do some of this analysis or to take this into consideration.
Correct. Yeah, that's true. And so I think our contribution is that there are previous wildfire risk estimations, but we're considering that physical aspect of the problem. We're considering it in a more detailed manner.
Thank you.
If there aren't any other questions, I have one about.
I have one more question on the the work you've done on spraying the retardants. That's the question. On how did you choose which retardant to use? I see the one you chose was made in Spain. Is there a method for you to choose these? Test?
We got that from CONAF essentially. So now CONAF is giving us another one. That I understand that's certified in Europe. I'm not sure if you're aware, but the most stringent regulations are from the United States, and European companies sometimes struggle to comply with the certification by the U.S. Forest Service. And so essentially, what CONAF had been doing historically was to abide to the, I mean, to only buy US certified products. But that means that your spectrum of suppliers is very narrow. But then you also run the risk of, if you decrease the level of certification, then you're gonna have access to more people, but then probably those are not gonna be as safe and as effective as the ones that are certified. So what we'll try to do now is we're going to go for the, I'm probably not going to say it, but it's the #1 brand in the world. And that is certified by the United States. So that we'll do that. But you know, the expenditure in Chile is high, where people, CONAF is moving to using more, but it's still something which is not, you know, so it's also part of like convincing them and all the people in CONAF to start relying on these products.
Yeah, in California, all the electric utilities are private concessions, and so that they have the same interest in this retardant as you do, because they spend a lot of money on vegetation management, and of course what they want to do is to lower the incidence of ignition, and you know, so they're willing to pay to test these products themselves privately to make sure that they work, and then but by doing it privately, they test what they want, right, at a certain level. But they are doing that. They are, you know, interested in these products and how they get done. So it's not a uncommon issue. But you explained it very well at how they chose it, how you chose this, yours.
Yeah, thank you. Okay. Thank you. And I think there's also like outstanding questions regarding how much, because these things are diluted. So you dilute them in water, and then you just, you know, drop them off planes or throw them from trucks. But I think we can also, we should, as a community, look more into what is the optimal concentration for actually being effective to fight fires. Maybe it's a little bit less, maybe it's a little bit more. We don't know yet.
Yes, and also the effect of rain on this, creating runoff that runs way beyond off, and there's a lot of good issues here.
And for that, I think that you guys in North America should feel really safe, because the regulations are really stringent in that aspect. Yeah.
Thank you.
Mm-hmm.
Yeah, I was going to ask if the U.S. was the most stringent because of all of those other things that it must do. Right?
Totally.
Suppress the fire, but because it has to be corrosive or not corrosive, and all the other environmental things that happen.
No, the list is huge to get that certification.
It's like a 40-page list.
Yeah.
Of all the things it has to do other than put the fire or, you know, suppress the fire.
Yeah,
so,
exactly. No, it's really good. It's really good. I mean, that's what I would recommend here, but then, you know, they would leave like 90% of the suppliers out of the of the bid, you know. So that they're trying to modulate that, you know.
Well, and what works, you know, when we're spreading it over the, you know, wilderness areas may not be what you necessarily need for the area near your power plant, for example. Like
correct.
So, kind of some different applications there.
Yeah.
Well, I have other questions, but I can refrain. We're right on time, so I'll respect everybody's time, and thank you once again, Pedro, for a very awesome talk. And it's great to hear from the other side of the world.
It's a pleasure.
Yep.
All right. Well, take care, everybody. Our next speaker is Chris Lautenberger next month. So look for the announcement on that and get registered, and see you then. Thanks, everybody.
Okay. Bye-bye. Thank you.
Thanks, Pedro. Great talk.
Thank you. Bye-bye.